Hey everybody, welcome to Math 30-2. Today we are on lesson 5 of the probability unit and we are going to be looking at conditional probability. And as the title suggests, we are going to be exploring how sometimes probabilities of outcomes depend on the conditions that the event occurs under. So let's get right into it by starting off with an example. And in this example, it's saying you are off to soccer and you want to be the goalkeeper. But that depends on who is the coach for the day. For example, Coach Sam, when he's on, the probability of being goalkeeper is 0.5. However, with Coach Alex, the probability of being the keep is 0.3. Now, the thing is, though, Sam is coach more often. So, in other words, about 6 out of every 10 games, or a probability of 0.6. So, when you show up to a game, you have a probability of 0.6 that Sam is the coach. And we have that illustrated in our little diagram down here. Let me get a highlighter here. So for 0.6 of the time, Sam is the coach, but that means that Alex is the coach the other 0.4% of the time. And remember that these are complementary events. It's either Sam or not Sam, which in other words is Alex. So when that happens, probability of Sam plus the probability of, just for ease, we're going to say not Sam, that has to equal to 1. In other words, 0.6 plus 0.4, we know that equals to 1. Now, going back to the information they gave us earlier, and they said that when Sam is the coach, the probability that you are the goalkeeper is 0.5. So when Sam is the coach, you are the keep. Yes, you are. And that means, going back to keep or not keep, that means we are just going to use our little formula. And we can use it this way. We can say 1 minus 0.5. And that's going to give us the probability of not being the keep. And we can put it like that. And so that means in this case, we have not keep like that. Now, when Alex is the coach, the probability that you're going to be the keep goes down. You're going to be, it's only 0.3, 0.3 is your probability there. So that means in this case here, that 0.3 the time you are the coach, but 0.7 of the time you are not the coach. I don't think this is a good color, but oh, that's low. But we get the idea. Now, the question's asking, what is the probability that you will be a goalkeeper today? Okay, well, that's a two-case situation. There are two cases where you will be the keep. You will be the keep in this branch right here, or you'll be the keep in this branch right here. And we can look at this kind of as that dependent probability that we were looking at in the last lesson. So what is the two cases? Well, it's the probability that Sam is the coach and you are the goalkeeper. Or the other case is the probability that Alex is the coach and you are the goalkeeper. So there's two cases. Now, these little tree diagrams are a great way of kind of organizing this. So that first branch, we have here the probability that Sam is the goal, and, in other words, multiply by the probability that you are the goalkeeper given that Sam is the coach. So we're going back to that dependent probability. And that, in this case, equals 0.6 times 0.5, which equals 0.3. And on the bottom here, that other branch we have right here, that's going to take care of the probability of Alex and goal keep, or in other words, the probability of Alex times the probability of goal keep given Alex has already been picked as the coach. So in that case, we're going to take our 0.4 times our 0.3 and putting that into our calculator, we get 0.12. So what do we do next? Well, remember in these types of probability questions, whenever we see the word or for cases, that means we're adding. So we're adding these two probabilities together, and that's going to give us 0.3 plus 0.2, which equals 0.42, which is the probability of being a goalkeeper today. So the probability of being the goalkeeper is equal to these two different cases added together. Let's move on to question 2. Now, the probability that Alex arrives home on time is 0.7. If he arrives home on time, the probability his dinner is burnt is 0.1. Maybe he has it in a slow cooker or something. I don't know why his dinner would be burnt when he gets home. But it's 0.1 that his dinner is going to be burnt if he arrives on time. However, if he does not arrive home on time, in other words, if he's late, the probability that his dinner is burnt goes up by 0.8. 0.8. So let's set up our little tree diagram again to organize our probabilities. So in this one right here, we have the probability that he is on time is 0.7, which means the probability of late equals 1 minus the probability of on time, which is 1 minus 0.7 equals 0.3. So that's where this number comes from. The next thing we want to look at are those conditional probabilities for being on time and having a burnt dinner, or being late and having burnt dinner. So when he's on time, the probability that the dinner is burnt is lower. It's 0.1, which means the complement of that is not burnt. And because these have to add up to 1, it can be 0.1 to 0.9. Now, we don't always have to show the work for these probabilities here, as long as we understand that they must add to 1. So these two here have to add to 1. These two here have to add to 1. And as you may guess, these here also are going to be adding to 1. So for instance, if he does not arrive on time, or in other words, he's late, the dinner is burnt 80%, or 0.8. I'm just going to erase this little square for now, which means it is not burnt 0.2. Okay, so in other words, he has an 80% chance, or a probability of 0.8. And remember, probability, we always work in decimals. Then we have the 4 outcomes. We have the probability of on time and burnt. We have the probability of on time, and we'll just use that complement notation, not burnt. The probability of late, which is just the complement of on time and burnt. And the probability of late and not burnt. So we have those right there. Now, before we move on to answering the questions, I just want to illustrate a point. And that is when I multiply the probabilities on the branches, so actually let's do this in the right order, 0.7 times 0.1, which equals 0.7 times 0.9. And then this one is 0.3 times 0.8 and 0.3 times 0.2. I want you to take a moment and calculate all of these probabilities. So pause the video at this point. I want you to calculate those probabilities, and then I want you to add them all together. Take a moment to do that, and then come back, and we're going to see what happened. Okay, so now that you have those probabilities, just check them against these. I got 0.07, 0.63, 0.24, and 0.06. And if we take those and add them all together, we actually, not surprisingly, have got one. So as a check to see if you're doing things correctly, you can check your probability. So again, these two have to add to 1. These two must add to 1. These two must add to 1. And then at the end, these 4 here must also add to 1. So if you set up your tree diagram, complete all the probabilities, you can check to see if everything is set up correctly and your calculations are done right if all of these equal 1. So now that we've set this up, now that we know all our calculations are correct, let's go ahead and determine what is the probability that Alex arrives home on time and his dinner is not burnt. So what we're looking for there is the probability of O and not burnt, which just equals, and I'll just write this out as our dependent probability. So the probability of O and is times the probability of not burnt, given that O has already happened. And that just really is repeating this line right here, which is, I won't do the calculation all over again, but it's 0.63. Now, what is the probability Alex's dinner is burnt? Well, that occurs in 2 places. That occurs here, and it also occurs here. So this is a 2-case situation. So it's, when does his dinner burnt? Well, it happens when he is on time and it's burnt. It happens when he is late and it's burnt. And remember, when we have the word or, we use add. And so the probability of or and burnt is 0.07 plus 0.24 for late and burnt. And adding those together, we get 0.31. Alrighty, let's keep going. Another soccer one. Whoever made this loves soccer. So Terry is a soccer coach, and based on the team's record, they have a 60% chance of winning on calm days and 70% chance of winning on windy days. I cannot verify the truth of this. I don't play soccer. I don't know if this is a thing. All the soccer people out there, let me know. So tomorrow there is a 40% chance of high winds. If there are no ties, what is the probability that Terry's team will win? Okay. So first of all, we want to figure out, what is the probability of windy? Okay. Well, it says there's a 40% chance of wind. So we are going to convert our 40% to probability. All we're going to do is get rid of the decimal sign and the percent sign, and move the decimal over 2 places. So that gives us a probability of 0.4. Now, again, calm is the complement of windy. So we're going to say that the probability of calm equals 1 minus the probability of windy. Like I said, we don't always have to show these. We'll do this every now and again just to keep it fresh. And so we get 0.6 right here. So that's the probability of calm. Now we're going to look at those conditional probabilities of a wind given it's windy, and so forth and so on. Now, based on the record, it says there is a 60% chance of winning on a calm day. So that means on a calm day, if we win, there's a 60% chance, convert it to a decimal, 0.6, which means there's a 0.4 chance that, or probability that there will be a loss. Now, for the windy day, for some reason, there's a 70% chance of winning. So that means converting to the probability, it's 0.7 right here, which means the complement of a win, which is a loss, is 0.3. Okay, let's put all of these things together. We have the probability of, notation is weird when we have windy and win. How would I just go to do the complement? Windy is not calm. So let's do it that way so we don't get confused with and a win. There we go. And then this is the probability of not calm or windy and a loss. And then the probability of calm and win. And then the probability of calm and a loss. Now, when you're doing these questions, you get to pick what letters you have for the notation, whatever works for you, just as long as it's you clearly identify what is what. Now, we are asked for what is the probability that Terry's team will win? Well, wins occur on two branches. It occurs here on the windy days and here on the calm days. So we need to know these two things because really what we're doing, we're finding the two cases where it's this or this. So we have that adding statement going on again. So what are we going to do? Well, let's write this out with notation, but we know that we can just go the probability of the windy or not calm times the probability of a win, given that it's windy. It's getting hard to say. Plus, that's that or piece. Remember the or is plus. The probability of calm times the probability of a win, given that it is calm. And just got to look at our tree diagram here. So the first branch is 0.4 times 0.7. So let's write that in. And then we're going to add to 0.6 times 0.6. Now, keeping order of operations in mind, we're going to do the multiplication first, and that's 0.28 plus, inside the bracket, 0.36, multiplication first. Now we're going to add, and we get 0.64. So the probability of a win equals 0.64. Let's keep going. Now, the next one is doctors use a test to find out who has a certain illness. The probability of a positive test, so let's kind of highlight some of this stuff, is 0.2. However, 15% of those with positive tests do not have the illness. Okay, that's called a false positive, by the way, and we're going to use that in the next question as well. So people who have positive tests but they're not sick is a false positive. And 5% of those with negative tests do have the illness. So that's a false negative. Okay, let's fill in our diagram. Well, there's two kinds of tests. You get a positive test and you have a negative test. Okay. Now it says the probability of a positive test is 0.2. So we're going to say it's 0.2. And the probability of a negative test, that is going to be the complement, which means we're just going to have 0.8, so that these two things, 0.2 and 0.8, add to 0.1, or sorry, 1. The next part of this is whether you're sick or not. So let's say that this one, we're going to call it, the two options after this are that is you're ill or you're not ill. And however you want to put these in here, then you're ill and then you're not ill. So it says 15% with positive tests do not have the illness. So the false positives are here on this one. So that's 0.15. Now the complement of that, if you need to put that in your calculator to find that, it's 0.1 minus 0.15, which is 0.85. And that's what's going to go up here. So this is the false positive, means this is the true positive. Okay. Now, on the other end of that, it says 5% of those with negative tests do have the illness. So that is the false negatives. So this is the false, oops, wrong letter first. That's the false negative, mean they're testing negative, but they are sick. And that's 5%. Now, remember 5%, if we're converting that to a decimal, we have to move it over twice, which means we got to throw a 0 in here, which equals 0.05 as a probability. So the chance to a probability looks like that. I made the mistake earlier of just putting 0.5 and none of my numbers added up. So it was like, okay, thought maybe I should point that out to everybody if I'm making the mistake too. Now, the next thing here is the true negative. Those people who test negative and are also not ill. And so that's 0.95. Okay, so again, remember these two add to 1, these two add to 1, and these two add to 1. Now, if you want to go ahead, and I think we will in this one because we're going to be using a variety of, or most of these, let's go ahead and do these calculations. So I'm just going to call it the probability of a true positive. Okay, and that's 0.2 times 0.85. And what do I get there? I get 0.017. No, sorry, I don't. Oh, yeah, I do. My bad. And then the probability of a false positive, meaning you test positive, but you don't have the sickness, that is 0.2 times 0.15. Notice I'm not putting in the notation here. Okay. We could do that, but we won't do it this time. And that is 0.3. And then the probability of a false negative equals 0.8 times 0.5, which equals 0.04. And then the probability of a true negative, meaning you're not sick and you test negative, is 0.8 times 0.95, which equals 0.76. Now, if we add all of these up, they're going to add to 1. So the question is, these are all probability questions. What is the probability that you get a positive test result and you are sick? So that is a true positive. So the probability that you are a true positive, and if you want to write those in, go ahead and, remind yourself that, this is a false negative, this is a false positive, and the other one is true. And so we have a true positive here. So you test positive and you are sick. Well, we know that is 0.17. What is the probability that someone has the illness? Well, that would be this one and this one here. So the probability that you are ill, that equals the probability of the true positive plus the probability of the false negative. And in the case there, let's see what I got. I got 0.17 plus 0.04. I'm looking at my notes now, realizing that I have made a second error, but I'm good here. So I'm going to add these together and I get 0.21 right here. Now, what is the probability that you are given an incorrect test result? Well, that comes from two places. That comes from the false positive and the false negative. So we're really looking, what is the probability of the false positive or the probability of the false negative? Okay. We know that the false positive is 0.3. The false negative is 0.04, which means the probability of this incorrect test result equals 0.34. Okay. Okay, so let's look at question 5. Very similar to the first one, or the fourth one. A test for type 2 diabetes measures blood glucose levels after fasting. A positive result indicates a level above normal. So if your blood sugar is above normal, that's considered a positive, meaning that you have type 2 diabetes. The test correctly identifies 85% of people with diabetes. In other words, 85% of people with diabetes will get a true positive and has a 10% false positive rate for those without diabetes, meaning you get tested positive, but you're not sick. Now, only 2% of the population has diabetes. What is the probability that a person who tests positive actually has diabetes? So let's set up our little tree diagram. Well, the first thing I'm going to do is break out our population into those that have diabetes and those that do not. So you can write it out if you want, or you can do some kind of abbreviation. It's all good. All right. And now we know this is remember 0.02. We got to move that decimal place over twice and then throw a 0 in the front, which means the complement of that, or not diabetes, is 1 minus 0.02, which is 0.98. Now, the next thing is that they have diabetes and the test is positive. In other words, that's the true positive. And we say that the true positive is 85%, which is 0.85. Now, what is the probability that we get a false negative, meaning that they actually have diabetes, but the test says they don't? Well, we're just going to subtract 0.85 from 1, and that gives us 0.15. The next part is we have no diabetes, and it's saying that we are positive. Well, that's that false positive rate that they talked about, and that's 10%, which means the true negative is the complement, and we're just going to take 1 minus 0.1 to give us 0.9. So if we want to kind of just put those abbreviations here, this will help us calculate the probability of the true positive. This will help us calculate the probability of the false negative. This is the probability of the false positive. And this is the probability of the true negative. Now the question again, what is the probability that a person has a positive test and has the illness? So that is, what is the probability of a true positive? Well, that equals the probability that somebody has diabetes times the probability of a positive, given that we already know they have diabetes. And that gives us 0.02 times 0.85, which is just really this branch. So again, I'm writing out all the fancy notation, but we can just kind of go off here if we wanted to. And we can check our stuff, remember, by making sure if we did find all these probabilities that they added an equal to 1. So putting this all together, 0.02 times 0.85, that gives us a really tiny number, and that is 0.017. So the probability that a randomly selected person tests positive and actually has diabetes is very low, 0.17, or in other words, you have a 1.7% chance of having diabetes. Well, that's the end of this lesson. If you have any questions, please don't hesitate to let your teacher know. I hope you have a great rest of your day. Take care.